as said, I'm a professor of intelligent user interfaces, and I'm a research group. I'm mostly interested in the question how we could utilize AI systems to improve productivity and well-being in safety-critical multitasking environments. And our projects are in the area of mobility and traffic safety, aviation, robotics, and manufacturing. But I mean, I will not put myself on the spot so much, because it's a great work of my dedicated team that does all the research, and I want to highlight them, of course, as well. So to get straight into the topic, I'll try to make it with the 30 minutes perfectly. We live in times of disruption and multitasking, and it's a bit of a risky question here in the US. It works perfectly in Germany or Austria, where I live. So who of you has used a smartphone in the car? Yeah, it takes some time, but many people do, despite what legislation says, because, I mean, these devices, they are somehow addictive, right? So it's just used to somebody sending us a WhatsApp and we need urgency to respond. And that is damaging to some degree. So we did different studies to find out how device usage affects users' performance and well-being. And I started with something different. So maybe you know this concept of the flow state, right? So it's where you have where you're concentrated, focused, and have high performance. To be in that flow state would require you to do a task for at least 10 to 20 minutes to get into that flow state. But due to all these disruptions we're facing today, we're hardly having the time anymore to really get there. So I show you some of the research we did in the past to find out. So this is a study we did on automated cars, where it is not going too well, never mind. How people would react to so-called takeover requests in an automated vehicle when they use their smartphones. So of course, the promise of automation is to make people use their devices in the car, but in certain levels of automation, it would still have to react to takeover requests, like a Tesla autopilot is not a fully automated system. You need to be able to intervene. And we did this with this balloon-inflated vehicle where people didn't know on which of the two lanes it would be when they would go around the corner, and we had to show their reaction. And we could see that, yeah, many people unfortunately crashed. So device usage in a car is definitely a safety problem. These days, and at least in European cities, it's a very sustainable alternative of mobility is cycling. And these days, even more people use smartphones while cycling, although they are much more vulnerable in that situation. So also here the question arises, how can we deal better with the kinds of distractions? But maybe let's get us into a scenario that all of us are more familiar with. So this is a study we recently did where we investigated people's behavior on workplaces. We did this at our university. We put people a camera glass on their head and we recorded them for 1 hour of work. And we then annotated the data with them. So we did emphasize privacy a lot. So in that sense, we, the researchers, never saw the videos. That's a video that I made from my perspective. So the experimenter was sitting on the other side of the table, and people were annotating their own video based on the instructions of the experimenter, and they could ask back if anything was unclear. What we wanted to find out is when, for what reason, people would switch between different activities, like I do here with alternating between my computer, my laptop, and so on. And management is not very happy when I showed them the results, because what we have realized is just for about 62% of their time, people actually work on the task that is dedicated to them. And what you can see on this time density diagram here on the right is, on average, these activities do not last longer than about 2 to 3 minutes. So at least one good thing is often people switch to something that is a bit work-related. So this could be gathering information on the web or talking to ChatGPT to get new ideas for your next paper whatsoever. But in nearly a quarter of these task switches, people went completely off task. Sometimes to, of course, respond to messages, sometimes to just watch a cat video. And the chances are always quite high if you're off task once that you stay there, because there is always another nice cat video coming into the reel. And so a question that arises, many people say, no, I'm not affected by that, I use silent mode. But what we're also seeing in that data is that people using silent mode, they even look more often on their smartphones because they want to know if somebody would have sent them a message already. So that's not the best idea. So one thing that we could do is to try to build something that counteracts these kind of developments. We know that these multitasking, task switching comes with high socio-economic costs. It's estimated that in the EU, about 1/3 of salaries are wasted through distractions. And as I said, there's a mentionable number of severe traffic accidents due to smartphone use. We can see the stats. That's, by the way, from 2014, the stats, 60 push notifications per day per smartphone. There must be newer data somewhere, but already that's a lot. So we know that task switches decrease our performance, lead to higher stress and error rates. So the question is, can we build some cooperative AI system, a so-called attention management system that would help us to better multitask? What this system could, for example, do is they could just slightly delay incoming notifications or interruptions to a better moment where we are more responsive. For example, when we're typing, when we have completed a sentence, so that we want to continue to typing later on, we don't have to find out what we're actually supposed to write here. Or there are other possibilities like in times of low cognitive load. And actually there has been a lot of research in the past working on these kind of systems. So at the CHI conference in the years from 2000 to 2010, 2015, you see many publications on the topic. But there are big problems to achieve these complex systems because the situation is difficult. Human behavior is very unpredictable. It's very context dependent and also task dependent. So the systems that were proposed use complex machine learning pipelines to, for example, detect in which state the users are in. They would detect natural breakpoints in the task, like end of a sentence kind of thing, and also to perform decisions. And this would require a lot of training data labeled by experts. And the question is, who would be an expert here? Who would know best for you when it's suitable for you to get an interruption or to switch between different activities? So these systems could also only become as good as the theories that these experts use for data labeling know. So we propose a different alternative to consider attention management as a joint human-machine optimization problem and using reinforcement learning to determine which task to attend and when to interrupt users. And that's quite a high goal, so we had to start very, very small and abstract. So this is the first example that we used in our system. It's a small computer game where you have to balance two balls on two platforms. You can only balance one platform at a time, and you use the shoulder button of your gamepad to switch from one task to the other. And these tasks get more difficult over time. So the ball gets faster, the platforms become more slippery. It's a bit like Tetris. At some point, you will just die. So the longer you're able to play this game, the better you perform in this multitasking situation. And so we've asked ourselves, could we train an AMS system, an attention management system, that would help you to become better by making the task switching decisions for you? There is a new problem that arises in that situation. So how could we train a cooperative AI that uses human behavior as the environment, as the testing ground? So, many millions of steps are typically needed for training. So I could put you all into our basement and let you play this game for weeks to train our system, but if something goes wrong, we have to repeat that task. So using real humans for the kind of training is quite infeasible. So what we need is simulated users, simulations of human behavior that play similar to real human users in that game, for example. And this is not only important for the systems we build. So any cooperative AI system in the future promises personalized interactions that are different for each of us, depending on our strengths and weaknesses. We need user models also to predict user behavior in different kind of situation. And one very big topic is also system validation of safety critical technology. So when you, for example, want to test a system like Tesla Autopilot, it's very difficult to put real humans in dangerous situations. But the dangerous situations would be the ones that you're most interested in. So when you have a simulation of a user, you may be able to better test these kind of edge cases. So human behavior models are important to build, and there is a new wave of systems trying to do that. Many people ask me, why not just apply deep learning or language models? I mean, these systems work very well for a wide range of tasks. But first of all, these systems lack grounding in human psychology. Often they generate a behavior similar to real humans, but there is no guarantee that they make it because of the same cognitive mechanisms as we do. They also have strong difficulties to work with out-of-distribution samples. So whenever you use the system in a situation it was not trained for, it might not work so well. And also traditional opaque models lack explainability that you might need to later ask, so why did this driver actually crash? Why did he or she engage in that kind of behavior? So thankfully, there is an alternative that is based on the following principle that I introduced by asking you, are we seeing reality as it is? Most of you would say, no, right? Because we are just a small biomechanical machine, let's make me say it that way, in our head. And we are limited by our eyes, by our senses, by our inner processes. And the brain just generates an image of what we believe is reality. And the concept that we use is called the computational rationality that works on similar principles by first of all stating that humans are not algorithmic agents. So we need to add something into AI systems that make them behave like humans. And computational rationality is one of the tools to do that. It has the following assumption that we as humans, we would always try to perform optimal given the limitations that we are facing. And limitations can be imperfect vision, like I had, or I could, let's say, have an injury in my arm. And so I cannot play tennis as the day before, for example. So computational rationality provides a framework to simulate these bounds in a reinforcement learning agent. You can imagine it the following way. If I would try to make a reinforcement learning agent play this game as perfect as it can, it would most likely never go game over because it could see the entire situation, could always react perfectly. But what I could also do is I could try to simulate eyes for my agent. So the agent would have to look around in the scenery to update where is the position of the ball, for example. How fast is the ball? As there are two balls on these platforms, I can only focus on one of these balls at a given time while I slowly forget what's happening on the other side. So our attention management system agents, they do not see the true environment. They see an internal environment that represents the constrained interaction space of our agent. I try to not become too complicated here, but our agent uses so-called belief state models that are partially observable Markov decision processes. So instead of seeing, here's a 2D version of it, the black ball where it really is, it would see a probability distribution of where it believes the ball would most likely be. And when the agent is, for example, distracted, like in that image, this distribution would flatten out a bit. So the ball could be here, could also be here, could a little bit here. But when the agent starts to really focus on that ball, we model a spike in this distribution. So suddenly the agent knows very well where this true ball actually is. And you can see this in this video here. There are two balls on the platform. And the green platform is the platform the agent is currently playing at, while the blue platform, the agent is not looking at. Typically, I say that there is this pigmented ball, that's the true ball, and there is this white ball lagging a bit behind that represents the belief state of our agent. Through to this technical issue, all the balls are lagging in this situation, but yeah, that's you can see it otherwise. What you can see, for example, well, here is on the blue platform, the balls are not in sync. They're always quite in sync on the green platform, but on the blue one, the agent forgets over time, where was the ball actually? What speed did it have? Where did it move to? So with that kind of system, we were able to generate a human behavior of a game player, and we used that simulated human to train our system for attention management. That's Alex, my student, who did this great work, and he's playing this game now with the suggestions of the attention management system that just switches between these platforms whenever it thinks that an intervention is necessary. So to test our system, we did a user study with 40-something participants, 43, I guess, who played this game in different modes multiple times until they went game over, to evaluate how our system could assist them. And actually, our attention management system could significantly increase humans' performance in that game, and participants performed up to 1.5 times better than in other modes. So we tested different kind of models. I will not go into the details here, but on the leftmost side, you see this kind of reinforcement learning-based attention management system that was trained on this cognitive model of a user. So, okay, now you might say, okay, it's a simple computer game. What does all that have to do with these situations that you introduced in the beginning? So, because for us, this was just a start. We continued with another project. So recently, we improved our system to work in a situation where you would have to manage incoming messages on the go. So you go to work in the morning and your friend is writing you and your wife is writing me, and I have to check what message is highest priority. Is it my boss or is it my wife? And the car is coming. So it's a tricky, uncertain situation. Could an attention management system here help as well? So in our environment that is now a clone of the WhatsApp application, we have multiple messages with different priority. And the goal is to answer these messages according to their priorities as fast as possible and as accurate as possible. And similarly, as switching between these platforms, an attention management system aimed at scheduling which message to reply to at what point in time. So this is an overview of the environment we use. So here we get a bit more complicated. So we built again a vision agent that is using a pixel stream of the environment to simulate the eyes of the user. And we also included a typing agent. So you can see on this kind of a small black eye on the screen, when the agent would look at the text, then it would better see what it has already written. But it could also look at the keyboard, and then it would hit the buttons more easy. When it's not looking at the keyboard, it might sometimes fail to hit the button. So you need to do a correction. So these kind of systems really work quite well to simulate real humans doing a messaging task. And on top, we have our supervisor agent who would then, again, control the ordering of messages. So these models, as I said, are grounded on principles in human psychology. So we use something that is called the WHO model for implementing typing. The WHO model just basically moves finger between different characters, and this models a speed accuracy trade-off. You can type very fast and do a lot of errors, or you can type very slow and be more precise. And you can control these parameters to model better and quicker typists. For vision, we use something is called the EMMA model that moves basically the gaze between different points of interest on the screen. And on top, we have our supervisor agent who would do the switching between the messages. Yeah, it has quite a complicated reward function. What is actually a weakness? Because we want to generalize in the future, we have to improve these kind of things. We did another user study now with that system. So here you can see one of our participants doing this kind of walking task that we used chalk to draw numbers on the floor, and people had to move different routes between these positions, and at the same time complete these tasks in the messaging environment, somehow replicate a real walking task. Of course, there are many things missing, like there are no obstacles, there are no dangerous situations, but of course we have to bring our experiments through the ethics approval, right? So we can't just do that. Maybe in VR at some point, let's see. The great thing is we could see the same result as we had in our computer game. So using our attention management system, people were significantly better in typing regarding the response, or also like typing performance parameters like words per minute or characters per second. We also had shorter reaction times when switching between these messages, and we also had less subjective workload using a NASA scale than in self-supervision. And that's somehow logical, right? If you're not burdened with the task of task switching and selecting the best message to continue, it's not that burdening. Also, the system was quite accepted in this mobile scenario. That was not always the case, because sometimes users also said, yeah, it's nice, it works good, but I want to be autonomous, right? I want to make the decisions. But in some of these safety critical settings, it's okay for users to relieve some of the burden to an AI system. What was even more thrilling here is that these computational models allow to adapt to different kinds of users. So the reinforcement learning policy adjusted to the typing speed of different users that we model. So for example, for slow typists, it's sometimes better to switch earlier to a message with high priority to not make it lie around for a long time. While for a fast typist, it's maybe better to let them complete the stuff before switching to something different, because they do fast responses anyway. And we compared this to different heuristics that we use, so like always switch to the task with the highest priority, and our systems was quite outperforming these things well. This is something that we work on now. So to go back to initial tasks that we had here, we don't use just messaging and messaging, but now again, typing while driving. And although it's forbidden on a smartphone, using an infotainment system to enter a navigation target, that's not necessarily illegal, or depending on which state I am. I don't know how it's in the US actually. So even if you don't use a smartphone, but just an infotainment system, you have the same kind of problems. And we haven't tested the system yet here in that scenario, but we would assume that it would work quite well too. There is one problem, so to say, with this kind of approaches that we have, because so far we only use human performance as an optimization target. And people sometimes say, yeah, okay, but there is more to life than performing good, right? Could this system be exploited by Amazon to make their workers work even faster in their factories, although they're unhappy already? And I acknowledge that. It's absolutely true. So what we're trying to do now is to engage more in this kind of multi-objective reinforcement learning. So one thing we want to do is we want to maximize the performance, but we want to use some stress measurements, for example, and minimize people's stress levels at the same time to find out what would be the policy that these systems then develop. But yeah, here things become a bit complicated, and if I would come back in a couple of years, maybe I can tell you more about how this ended. Another question that often arises here is like, how are you even sure that the models that you are building really represent human behavior? They just do something. And I mean, first of all, they don't have to be perfect all the time to make the agents they are trained on somehow useful, right? We see this in many domains, that also imperfect assistants can still help people. But we can also do studies to find out, based on distributions of responses, probabilities, and so if the data that we would collect when trying to see real human users operating in these situations with the same kind of measurements that we do on our agents. And to do that, we have different simulators in our simulator lab. So typically we build VR simulations for our tasks, and yeah, we have this driving simulator on the right that is built on quite cheap off-the-shelf gaming components. Students are really great, so they built like a real car seat foundation beneath it that you can electronically shift forwards and backwards. That's not included in what you can buy in this game store. And we have this bicycle simulator on the left where, yeah, we try to simulate different kind of things. Some of my students are mainly working on building realistic VR simulations. Yeah, and in the future we want to engage more in this kind of different work tasks that we're looking like. Here we have an example of a person collaborating with a cobot in an industrial environment, but doing a sorting task together, while at the same time doing calculations on the side, and these calculations will represent any abstract side activity people are doing. Yeah, with that, I think time-wise, I'm close at the end. So to conclude, I argue that user models like computationally rational models will drive the future of human AI interaction because they allow multimodal, personalized, and proactive systems, attention management and attention-aware computing. They will help to build simulated users for a wide range of systems to be validated, or they could also be used to just make digital twins of ourselves that could sometimes perform digital decisions or do similar stuff. Kind of this agentic AI system that people are talking about these days. Yeah, with that, I want to thank you so much for listening. If you have any questions, feel free to ask. Oh, Erin, you're late.
I'm not going to be here, so sorry. I got it.
Please, go ahead.
I'm really interested in the work that you're doing for simulations, particularly with VR. I've had a lot of experience in designing VR simulations myself, so I'm curious as to how you pick and choose which types of distractions to represent some of the hazards that some might experience in a realistic setting. Doing computational equations might not necessarily be representative of something that some might experience in a warehouse, for example.
Yeah.
So how do you pick and choose which is a viable or suitable distraction for those types of things, and how do you compare that with what one might experience in a realistic setting?
I mean, so far these simulations definitely have the issue of not being that realistic and not being that natural as you would expect it. I personally think that a lot of research that has been done in the HCI space in the last couple of years try to become more natural, but also suffered the cost of comparability and reproducibility. So what we want to do here is often to really find out what would be standardized tasks from psychology batteries that we can use. So for example, for driving, there is something that's called the lane change task, where you're seeing here. It works in a way that you would drive this highway and you would have overhead signs telling you which lane to go to, and you would have speed signs that would tell you which speed you should get. And you can then use this kind of system to get clear indications of how long did it take to change the lane, how fast were people to adapt the speeds. These are, of course, abstract tasks somehow, because in a real highway, it doesn't really matter if you're a little bit off in the lane, actually. But it's hard to judge performance in these settings otherwise. So we try to find something in the literature that can be used. Sometimes we get more natural playing back and forth.
Sure.
So using these user models to manage attention and performance, there's obviously a lot of practical applications. I mean, does your group look at any software products that you could spin off or that would help? You can imagine in work environments, but all kinds of environments.
Yeah, absolutely. So we are in contact with industry collaborators that we have. So in Linz, the city in Austria, where I live and where our university is based, we have one of the biggest steel plants in Europe. And they have different applications in that regard, like crane operators, operators of different kind of vehicles, drones. So sometimes you would have to control multiple drones at the same time. Ear retention management would help as well. But I mean, you could also see that we're still in a very early stage of developing these kind of systems. I would really hope that one of my students, when he graduates, thinks of creating a startup potentially with it. But I also have to say that the biggest lever for attention management is on these companies who provide the digital infrastructure, and by that I mean like Google, Microsoft, or Apple, because they are building the operating systems that control when notifications are sent, when interruptions work, especially for these everyday task environments we work in. And sometimes in this big socio-technic equation we think of, today that all the power is at Facebook or Twitter or OpenAI, and it's certainly true. They built these applications, but let us not forget who provides the infrastructure beneath it. So these companies could log out any of the other companies from their systems tomorrow, and then they're just gone. It's not something that I would suggest here, but it's like illustrating the power that these companies still have, although today we sometimes consider them as just the second line of computing.
They all support academic research. Have you thought of applying for grants from Google or Microsoft?
I haven't thought about that because, like, yeah, I work in Europe and it's kind of a different environment. But if you make me connect to these people, I'm happy to do so.
We have a question up. So, and
Please.
the question was about when you were talking about how these simulation lacks the understanding of psychology. So the question is that don't reasoning models currently approach some level of understanding of psychology?
I'm no deep expert in that. Don't get me wrong. I think language models are really cool tools that we can use for a lot of cool systems. I talked already before that we're currently thinking of how to use language models for better models that are grounded in human psychology. So typically we look at cognitive models from the past. And there are, for example, models such as ACT-R. Those are based on cognitive principles, but they have one downside. To simulate a scenario, you would have to handwrite a lot of rules that describe your scenario. What we think of could be a possibility is use language models to on the fly generate these rules for particular situations that emerge. This is, I think, a way to go when it comes to this psychological grounding that is based on theory, because otherwise a language model is still a big surprise box to me. Maybe I'm just not knowledgeable enough about them, but when I follow some people online who didn't know a lot about these things, they say the same.
There's one more question. So in the research that you do, do you need to gauge neurodivergence that is about ADHD early in your research?
I get this question often because people suffering from ADHD have often multitasking issues, actually. I would say that we don't do this yet because we have to be very careful in multiple regards. So on one end, we want to try to build systems that work for different kind of users, not just for the average user, so to say. I sometimes say each of us has at least one property that is a little bit off of the Gaussian distribution, right? So what these models provide quite well is they have parameters that you can tweak. And you can tweak these parameters in a way, as I showed you, to model good typists and bad typists. And with the bigger models that have many, many different components and complexities, you will certainly be able to also model neurodivergent capabilities. I think it's very important to address that in a way because the more parameters you have, the more simulations you need to represent all the users. And it's certainly a problem that when these systems can get bigger, you risk that you miss parts of the population in these kind of models. So this, but I would say you could write more than one PhD only about that for this kind of modeling. And yeah, you never know. I forget that. So at our university, we're also offering Fulbright exchange. So if somebody, a PhD students, would want to come to us and work with us, get into contact and do some cognitive modeling for ADHD and these kind of things.
Thank you so much for giving talk.
One more question.
Unless I want to hog unless someone else has a question. But my question is, I think one of the first studies you talked about was looking at task switching and how often people are switching within an hour, sometimes to on task, but sometimes to totally irrelevant things. And there are a lot of individual differences there. And some people are able to work continuously for quite some time without task switching. I wonder if you looked at any of the individual differences to look at what distinguishes those people who are able to work for a long time without task switching.
So there are some factors that would correlate with these kind of things that are based on personality types, but they also relate to how you would rate your own productivity, whether you would work on the morning or in the night. So sometimes that already makes a difference. Some people are more these kind of night owls, and some are very productive in the morning. So I will bring this question back to my students because it worked out as it always does. They collected this big data set, wrote a paper about it, and then forget what other interesting things could be present in that data. So certainly something to look into in the future.
Do you have more questions? Thank you again.
Thank you.
For speaking at BostonCHI, and thank you all for.
Thank you.